What we're going to talk about is, I feel like I just heard this presentation, but we're going to talk about how Talos builds a sequencer using Aeron. I think ours will be a little different. I want to preempt a little bit that, yeah, we're trying to build a business here. We're not in the business of just building technology that other people use. So there might be some trade-offs that we've made that are a little bit different than the ones that the real product might have in it. So, but excited to talk about it nonetheless. All right, I'm going to start a little bit and talk about what Talos is and what our business problem is that we're trying to solve. And so Talos is an institutional crypto trading platform that powers the full trade lifecycle. And so our main product is, if you're familiar with an OEMS, Talos builds a crypto OEMS and a lot more. And so what we do is we connect out to the entire crypto ecosystem, and you can access it via one API or one UI. And that means that we connect out to exchanges, so you can send orders, get market data, all the normal stuff. We also connect out, this is crypto, so we also connect out to custodians, so you can actually settle the trades that you've completed, all via one API. We think that this is what's really cool about digital assets, is that you can not only trade them, but you can also settle them. You can do that in real time. You can do that with finality because they settle on a blockchain. And this is real innovation. We think that eventually it will fall over into other asset classes. We think that all assets will be digital assets. So, picture of Talos trading. And then a little bit about how our technical architecture works. So we have a 3-tier architecture here, where on the right-hand side, we connect out to a lot of providers. I think we connect out to like 60-odd providers in the crypto ecosystem. So we do a lot of integrations. On the left-hand side is where our clients connect in. So they connect in via our APIs. We support a bunch of APIs. And have a normalized view of the entire ecosystem. And then in the middle, we have all of our business logic. And so we do smart order routing, we build trading algorithms, we do positions, we do risk. Some of our clients are on the buy side where they're using our trading algorithms. Some of them are on the sell side where they're actually like building, let's say, a crypto brokerage. And so you're trading with your clients, and then you're also hedging with the street. And then we have a whole bunch of other data products and stuff like that you might expect. Okay, and then I think a lot of Talos is built on kind of, I would call Aeron adjacent technologies. So we use Aeron as our main messaging transport, but we also use SB as our encoding. And so we have a lot of tooling built around this, like you might expect. Probably a lot of you guys are doing exactly the same thing. So we use simple binary encoding. We are big contributors to the Aeron Go port. So we didn't write this, but we must be the biggest users out there. We have a market data redistribution protocol that's built on top of Aeron. And so we always want to connect to the exchanges right next to them, so close to them. They're distributed globally around the world. So we connect to those exchanges. We normalize the data. We use Aeron to ship it across regions. Sometimes it's between colo to cloud. Sometimes it's between cloud regions, etc. And then the final thing we build on Aeron is a sequencer architecture. And so we just went through this, but I am going to go through our variant of this, which has a lot of similarities, a lot of differences. Ours is built on just the media driver and archive, so we're not going to be using cluster here. And I want to talk a little bit about how we got here. So what are the requirements that we have when we're building the system? So we're building a trading platform, right? We're not building an exchange, we're building a trading platform. And when you're building a trading platform, you might end up with an architecture that looks like this. We have a lot of services. They have these really complex data dependencies between them. This diagram's a joke, right? It's not really what we have. These are the data dependencies between the different services. We want to be very low latency. We shoot for under a millisecond across the system. It's not high frequency trading, but we want to be fast. We also think there's some unique requirements about crypto trading 24/7. This is not unique for this crowd because they talk about cluster a lot. And so we want to be able to, there's no downtime in crypto. There's no daily window. You need to have state recovery. You might have orders that are open for weeks on end. You need fault tolerance. Customers want to be trading all the time. So you need to be able to figure out how to do zero downtime upgrades. And then we also want to make the system easier to monitor and debug. And this is always a priority when you're building these kinds of systems. And then we think that sequencer architecture is a great solution for this, right? So we cleaned it up. So instead of having all those service dependencies, we still have all those services. They communicate via a single sequence stream, like we just talked about. This makes a really easy to understand architecture. It solves the low latency. We're using Aeron, so it's fast. I think that's one of the things you guys do. And we'll go through how we solve these other options around state recovery, fault tolerance, and zero downtime upgrades in a second. It's really easy to monitor and debug because we have tools. You can dump out the sequence stream, see all the messages. If you wanted to add something to asynchronously monitor what's going on in the system, you can do that. You can have no effect on performance. So it works out really well. All right. And now I'm going to spend some time going through how the system works and how we've built it. This is kind of a high-level diagram, and then we'll get into some more detail about how Aeron is used in this. So you can see at the top there, we have the sequencer, and its main job here is to sequence messages. So the main thing that it does is it builds that totally ordered output of messages. We have all of our services here. Sorry if you guys can't see in the back. Just let me know if you have any questions through this. We have our services to send messages. They send a message to the sequencer, and it is totally ordered. It gets sequenced. And then when a service wants to come up, what it will do is it will start. It'll connect to, it needs a snapshot to recover. So it'll actually go and it'll query the database. We just use Postgres for this. So we query the database, we get the state. We also get a position that you are in that sequence stream. And then we replay any messages that were missed and continue processing input messages as they come in. Just a couple other things to note here. We have, the way that we use the archive is that we are asynchronously archiving the messages. So the messages will be journaled asynchronously. We write those to disk. We have a couple of classes of services. So some of our services we say are kind of low priority. Mostly means that they do I/O and might have delays. And so they actually follow the sequencer recording. And then we have our real-time services that will participate in flow control. And so those are all reading the same sequence stream. Any questions there? All right, let's go. All right, and now I want to go into some details. So the cool thing I think this is so cool about Aeron is just how easy it is to take the tools out of the box. So take the pieces that Aeron gives you and compose them to build this system. And so the key things are, and just the number of tools that are in that toolbox that we're using here. So the basic pieces are the sequence stream. So there we use an MDC, so the multi-destination cast publication. We mostly run in the cloud, so we use that as opposed to native multicast. And then we have the archive set up to record that stream. We actually do it with one recording, and that means that every message that gets sequenced has a unique byte position, and we use that to resume and replay messages. Then we have our services. They just use regular publications to write to a well-known port that the sequencer is listening on. And so what the sequencer is doing here is it's taking images from each of those services, combining them into a single output image that everyone consumes that has that total ordering. This also does a couple of cool things. I just want to point out a couple of cool things here. So one is the way that, has anyone looked into replay merge? Does anyone know what that does? Yeah. Okay, cool. This is it's a kind of just a file that's sitting in the Aeron repo, and you're like, what does this do? But it does this really awesome thing where it solves the problem that we have here, where if you're a service, you want to start at a position, you want to replay all the messages from that position that are in the archive, and then you also want to go and process the live messages also. And it does this in this super, super elegant way. If you haven't looked at it, go check it out. I think it's something that's really unique to the way Aeron works with having byte positions in log buffers. And then the only other thing, another really cool thing we get out of the box is we actually often run this all on one machine. And this has the advantage here that you're doing this over IPC. We'll see some performance numbers. You can get pretty low latency without much help. And so we're using SPI subscriptions here if you're on the same machine. But you can also run it on another machine, and Aeron will replicate that buffer over once. And all the services on the other machine can read out of the same shared memory. And so there's some really cool features that you just get without much effort using Aeron to build these systems. Good. All right. Okay, here's a question we get. So why not just use Aeron cluster? Well, they didn't build the sequenced version of this before. So So we started in 2018. That's one reason. Aeron cluster was really in its infancy there, at least publicly. So it's all written in Java. We built this by Talos. We use a lot of Go at Talos, actually. But there is a more fundamental reason is around, do you favor consistency or latency? So in cluster, you're going to actually make sure that all messages are journaled on multiple replicas before they're processed. The way we've built the system, because we're a trading system, it fits better to our requirements. We'll actually process the messages before they're journaled. So they're journaled asynchronously. We have this advantage because often if we miss a message, or we crash, we can usually just go to the exchange, ask for the trades that we missed, and resume the processing. All right, cool. And then, there is a trade-off here. You have to build a lot of this stuff yourself. For example, our failover is still manual. You don't get the advantages of using the stuff that these guys have built. So this thing. Okay, and then I want to talk a little bit about service models. And so this is pretty similar to what we just talked about before. So we kind of have two that we use. So one is on the stateless side. So this is if you're a service, you can come up, you can store your state, or you can just be stateless, and you can ask the sequencer to resume processing messages as of an offset. And that's used by some of our API gateways. And then we also have the non-deterministic, a little bit of a legacy thing. I wouldn't suggest this, but we also have our services that are built deterministically. So this is the similar programming model to Aeron cluster. And here you come up, you get a snapshot as of a position, and then you recover state by reprocessing your input messages. And your services here are implemented using the deterministic replicated state machines. And that gives you all these nice properties around fault tolerance, downtime upgrades, etc. And I'll just note quickly, how does this actually work? How do you implement service level fault tolerance in a sequencer system? We didn't invent this. This is how a lot of systems work. If you have two copies, you're running active in service one. They are deterministic services, so they're sending the same messages, and then the sequencer arbitrates between them. So it just takes the first message with that sequence number, and that's the one that ends up going to the sequence stream. The other ones are just dropped on the floor because they're redundant. You obviously need to check to make sure the messages are actually redundant here so that your state doesn't diverge. But this has a lot of nice properties. You can obviously, if one of the services fail, you can continue on. But also if there's something like a GC pause or one of those copies of the services is snapshotting at the time, you'll take the earlier of the two messages. So it's a nice property that gives you flatter latency. Does that make sense? Okay. You can also get zero downtime upgrades this way. And so to do that, you need to leverage feature flags. You need to upgrade. You can upgrade one copy of the service, then the other replica. And then once they're both upgraded, you switch the feature flag on that enables the new behavior. All right, and here's some performance numbers from this. So we're cheating a little bit here in that this is all over IPC. So these are in memory. It's not actually going through transport here, but you can get with Aeron, you can get very nice in-memory performance numbers. This is actually a client and server. So we're sending a message to an echo server so that goes through the sequencer, and then the echo server is responding back. It's all over shared memory here. So it's not really a fair comparison with some other metrics. All right. And just a couple other cool things I want to mention is on DR. So this is the primary backup, similar to Aeron cluster backup here. So we're not running active, but we can replicate the recording just like you would. So from a primary region to a secondary region, we also do the same thing for the database. And if you replicate both of these, then you can do a failover to fail over the sequencer from one to another if there's an issue in one. All right. Okay, cool. And then looking forward to some of the things that we're building next that we're focused on. One is running sequencers in multiple regions. And so actually what this is because, crypto trades everywhere. Most financial services are actually like this. We have exchanges across the world. We want to be running our logic close to them. So we want to be able to bridge messages back and forth between two sequencers that are running different sets of services, but you still want the data available in both of the regions. So that's something we're working on. I think the second one, fault tolerance, I think you guys have a good answer to that one. So let's just check that one off the list after today. And then number 3 is something we call quality of service. And so this is thinking about, it's really easy to build a system. It's really easy to write a service where it just spams the system, and building these features into the sequencer so it can do things like throttling, so you can have quality of service where you might be backfilling trades at the same time there's real-time orders coming through the system, and you want those backfills to be slower and not overload the system. So there's a couple of things that we're working on. All right. Okay, and just wrapping up here. So I think these sequencer systems, they're great for some sets of requirements. It works great for us. And then Aeron makes it really easy to build these kinds of systems that are really high performance. I think one of the Aeron values is about building libraries, not frameworks. I think maybe Todd or Martin said that at some point I saw. And I think the testament of how easy it is to build this using the pieces that they have, and how you can build your own system that has your own requirements and do that really easily, is really a testament to the quality of the open source libraries here. That said, there's a steep learning curve. You can ask the team. This stuff is not easy to build. It's not easy to get right, but it's definitely worth it to get the kind of performance and reliability that we want when we're building systems in the cloud.